because all kinds of energy, whether electrical or chemical or mechanical, can be expressed in the same units, joules or foot-pound force, depending on our unit system, we can build pretty easy conversion models and do analysis in a pretty simple manner about any type of energy conversion. But before getting to some examples and discussing all the different ways that energy is converted and transferred in various processes, I do want to push you to page 78 in the textbook that just kind of talks about the energy that the Earth receives from the sun every day on the order of 10 to the 24th joules, what that does for the planet, how we make use of it, and then to consider what happens if we end up with an imbalance of the energy that is being received versus radiated away. So I do encourage you to spend a little bit of time there since this may come up in a future context if you understand my meaning. So in the context of the Earth, we can think of it as an isolated system in which we're observing energy changes. We can do a similar type of analysis when it comes to all sorts of systems, like consider a car. So we pump gas into a car, so we are providing chemical potential energy into the vehicle, and so then we have a whole series of different types of conversions, energy conversions that take place. We take the chemical energy from the gas tank through combustion, that drives piston movement, which then gets transmitted via crankshaft and axles to the wheels, which then takes us to movement down the road. So we go from potential energy to kinetic energy to rotational kinetic energy, back to kinetic energy, not to mention all the other things that get powered in a vehicle. So we have all sorts of forms of energy conversion that takes place through this process. Now, ideally, all of that energy that we're putting in, potential energy in the form of the gas that we're putting into the gas tank, will be used to help propel the car down the road. But as we see in this next example, that is not necessarily the case. And so if we take a gallon of gas that has approximately 1.3 times 10 to the 5th kilojoules, so that would be 1.3 times 10 to the 8th joules chemical energy. We want to know how many gallons of gas would be the equivalent to a 1,000 kilogram car traveling at 65 miles per hour. So we're assuming all of the energy in the gallon of gas would be transmitted to kinetic energy. So we don't have just an equation that we're going to use to solve here. Instead, we're going to have to use a little dimensional analysis to piece things together. So again, we know that we've got this 1.3 times 10 to the 8th joules per gallon of in a gallon of gasoline. And then we know that our velocity is 65 miles per hour. So those are really the only two pieces of given information along with the 1,000 kilogram mass of the car. So if we think about the kinetic energy equation that we have, we can start there. So our TKE in this circumstance is going to be 1/2 times the 1,000 kilograms times the velocity of the car, so that's going to be our 65 miles per hour squared. But we're going to have to do a series of conversions here. So we've got our 1 mile to 1609 meters is our standard there. And then we've got our very common hours to seconds conversion that we need as well. So when we multiply that all out, we end up with a kinetic energy of 422,000 joules, or if we wanted to convert it to kilojoules to match up with what our gasoline potential energy is given to us as, 422 kilojoules. So how much gasoline would we need to have that same amount of energy? And so we can balance this out. So we've got our 422 kilojoule energy for the kinetic energy. So we need to have a commensurate amount of gas. So we have X gallons times the 1.3 times 10 to the 5th kilojoules per gallon. And so we can see that if we divide both sides by that 1.3 times 10 to the fifth, our kilojoules will cancel out. We'll be left with gallons on both sides. So we end up with X equals 0.0032, again rounding to two significant figures, gallons of gas. Now if we think about that for a second, we're saying that to get a car, maintain a car traveling at 65 miles per hour down the highway, it's only going to require 0.0032 gallons of gas. That's just not realistic. And so what we're missing here is the idea that there's a lot of energy loss in all of the conversions from the potential energy of the gallon of gasoline to the kinetic energy of the car traveling down the highway. Not only do we have a lot of energy loss in all those conversions that we saw previously, from the gallon of gas to the pistons moving to the rotational movement to the kinetic, translational kinetic movement of the car, but as I mentioned, there's also other things that need to be powered by that gasoline. We've got the air conditioning or the heat, we've got the stereo, we've got the lights, the braking system. All of these things are being powered by the energy that's being supplied by the gasoline. So the idea that it's just a one-to-one conversion, even if we adjusted for some of the loss, would not be accurate. So we need a little bit different model. So instead, let's say a car that's traveling 65 miles per hour requires about 80 kilowatts of energy in all sorts of forms. So again, for all those different purposes, not to mention the loss. So we have that same 1.3 kilojoule times 10 to the fifth kilojoules of chemical energy supplied by the gas. So now we want to know how many gallons must be used per second to provide the power needed to sustain that 65 miles per hour. So from that, then, we want to figure out what is the approximate miles per gallon. So again, we don't really have an equation that's going to help us here. We're going to have to work with the units of the various disparate parts of information and try to piece something together. So if we just look at the units of everything that's given to us, for the speed, we have miles per hour, so we have distance over time. For the power, remember that kilowatts, a watt is a joule per second, so I'm going to express that as joules per second, or kilojoules per second if we want to stay consistent. And then, of course, here in the 1.3 times 10 to the fifth kilojoules of chemical energy, that's per gallon. So we have kilojoules per gallon. And so for our first question, we're asked to find the number of gallons per second that are necessary. So as I see here, these are my units that involve the gallons and seconds that I want. So how can I end up with gallons in the top and seconds in the bottom? Well, what I could do is I could take that first unit and divide it by the second, because if I divide it, I'm going to flip the units on that second term, so I'll end up with gallons in the top and kilojoules on the bottom, and so then my kilojoules will cancel each other out. So if I divide those quantities, I'm going to get that kilojoule, or that gallons per second that I'm needing to answer this question. So if we do that here, I've got 80 kilowatts, and again I'm expressing that as kilojoules per second. I'm going to divide that by the energy in the gallon of gas, so that's 1.3 times 10 to the fifth kilojoules per gallon. And so when I divide that, my gallons are in the bottom of the bottom, so they're going to end up in the top. My kilojoules are going to cancel each other out. And so if we divide those, we're going to get 6.15 times 10 to the negative fourth gallons per second. And again, that's a very small number of gallons. I don't know if that's realistic or not. I don't have a whole lot of experience with trying to measure how much gasoline is necessary to maintain this kind of power requirement. So if I can convert this to a context that I have a little bit more familiarity with, like miles per gallon, that I'm going to get this gallons per second into, then I can determine whether or not this is a reasonable estimate. So again, I'm going to look at the units I'm working with. So I've got my speed here is miles per hour. So I want to end up with miles in the top, so that's a good start. But I don't want time, I want gallons. But if I look over here, I've got gallons over time. So once again, if I divide those two, if I have miles per hour divided by gallons per second, I'm going to end up with my time in the numerator of that second fraction. And so with a little unit conversion, I'll get the times to cancel out, and I'll have my desired result of miles in the top and gallons in the bottom, and I'll get an estimate of the fuel economy of my car. So I'm going to take that 65 miles per hour, and then I'm going to just multiply it by the reciprocal of this quantity here that we calculated. So we've got 6.15 times 10 to the negative fourth. That's going to be gallons on the bottom and seconds on the top. And then I've got my miles, I've got my gallons, but I don't have my times canceling out right now. So I need that conversion factor of 1 hour and 3,600 seconds. So now I can see that my hours will cancel out, my seconds will cancel out, and I'll be left with my desired units of miles per gallon. And so if we calculate that out, push buttons on our calculator, we end up with 29.3 miles per gallon, which, if we pay attention to what our cars get now, seems like a completely reasonable answer. So this is an example of how we can track the energy conversion from a gallon of gasoline to the kinetic energy, but also incorporate some of the other features that are powered by that gasoline, not to mention the energy loss. And so by just analyzing the dimensions, the units of all the quantities that are given, without having a specific equation, we can manipulate them around in such a way that leads us to an estimate of what the fuel economy of a car is in this case.